Hi, my name is Mark Dittmer, and I'm an Algebra 2 teacher at American Indian Model Charter High School, public charter model school. And this is a video about trigonometric functions. It goes slightly with section 14.1 of our Algebra 2 textbook. And that section, 14.1, is a huge section and talks about how to graph every single kind of trigonometric function. We're going to talk in this video only about the sine function. And so our objective here is to graph the sine function, y equals a sine bx, and to find the period, midline, and amplitude of sine functions. And remember, I'm going to move kind of fast, so pause me if I'm going too fast. Like, just hit the pause button. So, basically, what most of the learning here is right here. So what you want to do is first look over on the far, I guess your left side of the screen, at the circle. That's where we're used to seeing our angles measured, right? I mean, of course, we see them in just triangles, but we plot them on the unit circle, and it just so happens that at every point on the unit circle, x is cosine and y is sine. That means that y is red. So at 0 degrees, y is 0. And as we get closer and closer to 90 degrees, y gets closer and closer to 1. Now, there's lots of different levels you can think about this on. The first level is SOHCAHTOA. Sine is opposite over hypotenuse. So the red line is the opposite, and the gray line, the radius, is the hypotenuse. So, and you have a little triangle there, right? So you see why I'm talking about opposite hypotenuse. And you have the angle on the inside represented by this curved line, where I might just move the mouse to. So over here, opposite is very small, but the hypotenuse stays the same, right? Opposite gets closer and closer to 0, so sine gets closer and closer to 0. But as opposite gets bigger and bigger and bigger and bigger, it gets closer and closer to being as big as the hypotenuse. Until, when I go right here, it is as big as the hypotenuse. There's no triangle now because the opposite side is like right on top of the hypotenuse. It's just a line. But since opposite over hypotenuse and that you've got the same something over itself, 1 over 1 or whatever, that means the sine is 1 at that point. So if we go from just looking at these angles, it goes 0 to 1. That's what happens to sine. And then sine stays, what we started to learn about a month ago is that sine stays, we keep track of sine over here also. Now my angle is obtuse, but I can still think of it as the y value on these coordinate pairings, and so now it's still positive, but it's less than 1, right? So really, here at 120, sine is the same as it was at 60, 0.866, 0.866. And that's always true. You can always, if you want to find what the sine of 100 is, we'll just think, well, what's supplementary to 100? 80. So I go to 80, and it has the same sign. So because a circle is symmetrical, it's always reflected across that y-axis. 60 will be the same as 120. The signs are the same. And so then the sine gets lower and lower and lower, and it gets to 0 again here. And then we have something new happen. And maybe you notice it. It's that the sine is now negative, because y is negative now. Now we're moving into negative territory. So now the sine gets to be negative, and it gets, how far negative does it get? It gets all to a maximum negativity of -1, and then it starts to come back to 0. Okay, if you, I've just been looking at the circle over here, as I've talked about this. I'm just looking at the red line, that's the sine, and I'm looking at its value up here, and it starts at 0, goes to 1, goes to 0, goes to -1, and then goes to 0. And all the while, the angles are not, notice that this graph of the unit circle, x is on the x-axis, y is on the y-axis. These angles are not on either axis, right? They're on this, being measured on the unit circle in this new way that we're not used to. So what we're going to do in chapter 14 when we graph these functions is we're basically going to unroll the circle. So if you imagine that circle unrolling, and let me draw you a picture. So here's my circle. Let's say there's let's just break the circle open and let the circle start to unroll, and we'll just in fact, now it looks like a sort of like a hair sticking out, and let's just move the hair. Let's just extend it straight up. Now a little curve left in it. And now let's just lean it down straight on the right. And so here's some labels to see what the heck I'm trying to show. Basically, imagine that unit circle, the 0, the 90, the 180, and we sort of break the circle and lay it down on the x-axis. That's what we're doing here. And so now we're actually graphing the function with 0, with the degrees on the x-axis, and the actual value over here on the y-axis. And what we've got to do, just to learn one thing at a time, is just with your, and I would show you this if I had it, but I don't. So I would show it to you with just the sine. So just block out the cosine, which is blue or black, and the tangent, which is green, and just focus on the red. That's the sine. So as we're going around the circle now, you see how that function goes up to 1, and then down to 0, and then down to -1, and then back up to 0. Kind of a perfect wave. And then that goes from 0 to 90 to 180 to 270 to 360. Now, if I had more room on the graph, it would go on to 370, 380, 390, 400, 415, 420, 430, 440. But it would be the same y result. So I could be going around the circle a second time, a third time, a fourth time, and the graph will still look exactly like it looks over here. So this exact thing repeats itself, which is what makes it periodic. Okay, so that is the graph of y equals, and you saw on the in the objective it said the function is y equals a sine bx. Well, so y equals a sine bx, but in this case it's y equals, we're not, a and b in this last one, a and b were just added on to this. Really all we did was plug in a value and sign it and see what happens, is what we were doing, right? So we were just not really using this. So without the a and the b, we have y equals a sine x. And so to graph that, we're going to let's get rid of the unit circle. Let's say y equals sine x. And there it is, sort of the same thing that you were looking at on the other page. Up to 1, down to 0, down to -1, up to 0. So if you look at it, like a good way of thinking of the graph is thinking of it in those 4 parts. And that's a good way of translating the circle. The circle has 4 parts. So from 0, the y goes from 0 to 1, 1 to 0, 0 to -1, -1 to 0. And over here, the graph has 4 parts. It goes from 0 to 1, 1 to 0, 0 to -1, -1 to 0. So that's one way of looking at this. The next thing to do is to answer some easy questions. One is, what's the midline? Well, remember the midline just cuts right through the middle. This thing maxes at 1 and minimizes at -1, so the midline is going to be y equals 0. That's the midline. And the amplitude, what's the amplitude? Well, remember the amplitude is the whole range, in this case, from 1 to -1, that's 2, divided by 1, so the amplitude is 1. The amplitude is 1, so the amplitude of the sine function is 1. How would I get a bigger amplitude? Pause and think about it, because I'm about to tell you in the video. But how would I make this function stretch so this goes up and this goes down? Well, put a right here, add slider. Now, if I make a bigger, what do you think is going to happen? So if you thought that's going to make the amplitude get bigger, you were correct, right? So that's y equals 2 sine x right here. Same place that it hits 0 right there. Same place where it hits 0 again right here, but different. So the interval is the same, but the actual distance it travels, how high it gets, is different. If I go, this is back to the way it used to be. A little different. Okay, so the y on the sine functions is easy. Figuring out, what the amplitude is, and those values. It's like the y values are nice and easy to 1, 0, -1, 0. Those are easy. The x values are harder. What the heck are these x values? So, well, let's look at this. What are the x values? Oh, they're degrees. Okay. But degrees, remember, what's a degree? It's this random unit that the Babylonians came up with because they liked base 60. So they randomly decided that the circle should have 360 degrees in it. But our better measure is radians. So make friends with this picture here. Know your radians. So it's not 0, 90, 180, 270. It's 0, pi over 2, or 1/2 pi, 1 pi, 1.5 pi, 2 pi. 0, a half pi, pi, 1 pi, 1.5 pi, 2 pi. And then lots of in-betweens. But that becomes, when we unroll the circle, then we don't have 90, we have pi. Pi over 2. And we don't have 180, we have pi. And that's important because when we bust up our graph into its 4 parts, we're going to want to make sure we graph it correctly. This is going to be 0, but that's going to be pi over 2, and this is going to be pi. And if you want to see that, we'll look right here. So that's pi over 2. Oh, wow, Desmos has already figured that out. And this is pi, 3 pi over 2, 2 pi. What's the period of this function? Well, the period is, remember, how long it takes to repeat itself. And it takes 2 pi. This takes 2 pi. Can I change the period? Change this graph horizontally like I was changing it vertically with A? Well, you might have guessed that that's where this B comes in. Okay, so if B is 1, it's the same. But if B goes up, then what happens? What do you think happens? So you can play with this. Again, you go to desmos.com, type this in, add slider, and mess with it yourself. And see if you can get an idea of how B affects the period of the graph. Again, right now the period is 2 pi, 6.28. That's the period of y equals a sine x when B is 1. But what if B is something else? Will that make the period bigger? Will that stretch it out horizontally? Stretch it out horizontally? or compress it horizontally. So find out for yourself.